Mic check. Can everyone hear me? Hello, hello. Hi, Betsy. Hi, Brandon. Hi, Kayla. Elizabeth. Casey, read yet? Welcome in. Let me know if you guys can hear me. Thanks, Elizabeth. All right, all right. It's 6 o'clock. So let's see. I'm gonna wait just a little bit, but I think we're gonna get started very soon, everybody. We have a lot to go over. How's everyone feeling? How we doing? Feeling okay or stressed or somewhere in between? Are you feeling good or kind of stressed or somewhere in between? Let me know. Kayla says good. Elizabeth says good. All right, all right. Casey says dead. Okay, okay. All right. What's the hardest thing for everyone? I saw a lot of comments saying saying resonance, got a lot for resonance, got a lot for naming, got a lot for um Um, Lewis structures, what's the hardest thing for everyone? What's like one or two things that's like the hardest thing for everyone? Knowing when to use Vesper theory, naming, geometry and shape. Yup, yup, yup. Lewis structures. When there's more than two atoms involved. So basically the um Lewis structures. Okay, okay. When there's two more than two atoms involved. Polyatomic ions, right? Polyatomic ions. Isaac, welcome in. Redia, welcome in. Briseida, welcome in. And then also naming. So those are you that are just joining in. Let me know what's like the hardest thing for you. What's the hardest thing for you? And then I think I want to wait like a couple more minutes max, and then I want to jump right into it, guys and gals, because we have a lot to go over and we don't have that much time. Okay. So I'm gonna start sharing my screen and think we're gonna get started via CPR theory. All right. Can everyone see my screen? Let me know if you can see my screen. Let me know if the audio is good. So thank you, Kayla. Thank you, Elizabeth. All right, everybody. So cool, cool, cool. Yeah, yeah, yeah. I think we're gonna get started because we have a lot to go over. And it's 6:03. Casey, thank you. Jivan, welcome in. All right, guys. So yeah, as people are chiming in, I'd like you to again let me know like what are some topics you'd like to see, and yeah. So let's get started. Let me we're gonna have like a combination of let me drop in the slides too, so everyone gets a copy of the slides and. Everyone's gonna get a copy of the recording, so I'm recording. So if you guys don't want to share your screen, that's fine. Or if you do, or if you want to unmute yourself, that's fine too. This is like gonna be, semi-formal, semi-casual. So dropping in these slides here. So at any point you wanna interrupt, ask your questions, that's fine. There's not that many people. So if you want to interrupt, ask your questions, just comment or just unmute yourself. And great, 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 great. So let me know if everyone got the slides. They're not the most amazing, but they have a bunch of practice problems, as many as I can add, okay? So great, great, great. And I like to make this really, really interactive. So comment down below. Comment a happy face emoji or a crying emoji. How are you feeling about this midterm? So if you feel that you're feeling good for this midterm, or pretty good, or at least okay, comment a happy face emoji. Or if you're feeling not so good, okay, and you're feeling cooked, mega cooked, fried, or Korean barbecue, put a crying emoji down in the chat. So if you're feeling pretty good for tomorrow's exam, or if you don't have an exam tomorrow, generally, if you're feeling good about Gen Chem, put happy face and then crying emoji if you're feeling not good. Okay. Hi, Jamie. Welcome in, Jamie. Okay, Jamie says crying. Brandon says, I don't even know what that is. Isaac says dead. Someone else said dead. Casey says totally burnt. All right, all right, all right. Elizabeth is in the middle. Reset is crying. Red is happy. Brain is crying. Okay, good mix of everyone. All right, good mix. So that being said, there's a couple of ways we can go about this. And here's the original agenda that I had because I understand a lot of you have chapter 3, chapter 4, chapter 5, And then those of you that don't go to UCR, hopefully this one is still going to be helpful for you still too. So chapter 3 is atomic structure, chapter 4 is molecular chemical bonding, and then molecular geometry, and then practice problems, and then remaining hour Q&A. So let's call this like lecture style. This was the original intention, was lecture style. And then option number two, um, um, is going to be office hour style. So, next question is comment a happy face if you're like, hey, Drew, I'm so cooked. I need you to start from the beginning. And then you're going to vote for a happy face. This is going to be lecture style. And then comment crying emoji is like, you know what? We don't need to start from the beginning. I just need some examples and some practice problems. And I need some questions. Like, this is going to be office hours. So I'm going to comment crying emoji. That's my vote. Okay, I'm gonna comment crying emoji, but I want to see what everyone's thinking. Casey says happy. Casey says like I need you to start from the beginning, Drew. Like I'm so lost. Okay, so some people are like lost, some people are like in the middle. All right. Thank you, Betsy. Thank you, Reddit. And then again, guys, I am gonna be recording this, so everyone attending this is gonna get the recording, or I'm gonna post it on YouTube later today. All right, thank you, thank you. So yeah, I think what we're gonna do, guys and gals, we're gonna do like a hybrid. Channel link is gonna be, yeah, let me drop that. Let me drop that right now. I think what we're gonna do, the plan therefore is gonna be we're gonna do a hybrid. So we're gonna kind of start from the beginning-ish. Because I had a feeling, yeah. Some of y'all are like, all right, not too bad. And then some of you are like, hey Drew, I really need a refresher. Okay. So what we're gonna do is kind of hybrid. And we're gonna skip around a lot, okay? We're gonna skip around a lot, but you have the slides now. I just dropped the slides in the chat. So now you have the slides. So whatever I don't finish, doesn't mean that it's not going to be covered on the exam. So we're going to do our best to do as much as possible, right? All right. So, yeah. So there's a lot of different topics that we can go over. And then, yeah, without further ado, my name is Dr. Drew. And yeah, my company, guys, is called Engineering Minds. So those of you that are from UCR, I went to UCR too. So, super honored to be doing this live today, guys, because I actually had Dr. Hill for undergrad in my freshman year, all the way back in 2015. The only difference, I had Dr. Hale for Chem 1B. So I know we're doing Chem 1A right now, Gen Chem 1, but I had Dr. Hale for Chem 1B, and I actually got cooked so hard on the first midterm, and I did even worse on the second midterm. So to be, here, 10 years later, like helping students out, that's why I'm really passionate about like teaching guys. And so, yeah, I'm building out this company. I ended up doing my PhD and kind of shifted the switch, guys. I learned how to study it, develop my study skills, so that's why I'm out here doing what it is that I do. So you can book a free strategy session, a link in my bio, link in my website. And then guys, I have practice problems on TikTok as well. So lots of Gen Chem, OChem, physics as well. Okay, and then one more thing. Can everyone just comment down your major and what year are you? Year and major. And yeah, what's your year and major? And then now we'll get started. Okay, Brandon. Okay, it's like first year. Okay, cool. We're gonna get started. We're gonna get started. So, like I said, we're gonna go quickly. So, we're gonna skip around a lot. All right. We're gonna start with atomic structure, and yeah, kind of this stuff is like I think this is the last midterm, so we're gonna skip over. But I still want you to not forget the concept of light and photoelectric theory, guys. Okay, so this is still gonna be important. So, just a quick little practice problem. What is the value of RH in the Rydberg formula? Is it happy face? 1.0974 times 10 to the 7 inverse meters, or is it crying emoji? 1.07974 times 10 to the minus 7 meters. Comment down below. Comment down below. So don't forget, I don't know if this is going to be on your final tomorrow per se, but it's still going to be important. So if it's going to be happy face, it's going to be RH is positive 7, and then if it's crying emoji, you're going to say negative 7. Okay, don't be shy. Don't be shy. You can just guess. You can just guess if you forgot. Okay, does everyone forget? Everyone forget? There we go. Got a couple for crying. Got a couple for crying. Okay. So look at the units, guys. Okay. So everyone's saying crying. Am I mistaken here? I believe this one's gonna be happy face, guys. Okay. So we have the positive 10 to the positive 7 with an inverse meters here. Okay. So just a quick little reminder. So yeah, we're gonna like I said, we're gonna skip over everything here. Okay. Yeah, inverse meters. Yeah. Yeah. Okay. So we're gonna skip over the Bohr model, but again, I want you to understand that electrons live in the discrete energy electron orbitals here. So the electrons live in electron orbitals, and then this is called the Bohr model. We're gonna skip this, we're gonna skip this. We're also gonna skip this one. Again, I think this was the last exam. Okay, but everyone's been asking me about this one. So this block, another one here. This block corresponds to what? Is it the happy face P block or D block, the crying emoji? So this block here that I highlighted here in red, is this the P block or the D block? Comment down below. Okay, so there we go. We got more votes. There we go, guys. There you go. Good job. Good job. So everyone said D block. Good. Okay, so don't forget this stuff. I don't know how much of this is going to be on it tomorrow. That's going to be D block. Okay, so if you want to review, I dropped the slides. To review the slides, we're going to move forward. We're going to move forward. We're going to skip atomic size and orbitals because I want to get to Lewis structures. Okay, the only thing I do want to tell everyone, we're going to skip this, but the only thing I do want to tell everyone is orbitals are just electron bubbles. So you don't really need to worry about this stuff too much. I just want you to know that the electrons live in these orbital thingies and they're just kind of like these bubbles, right? Right? Does everyone understand this for atomic theory and quantum theory? It's not it's very theoretical, so we don't have time to go through the theory here. Okay. All right. Here's our next one here. Okay, here's our next one. So what is the electron configuration for iron? How do we do electron configuration? Is it happy face 4s2 3d4 or crying emoji 4s2 3d6? Okay, how do we do these? Comment down below. Comment down below, how do we do these? So first things first, I'm gonna bring out my periodic table, right? I'm gonna bring out my periodic table. Oh no, I don't think I have my periodic table. Okay, this is gonna be good enough. Okay, so to do these, I need to locate where is iron. So iron's gonna live right here. So the previous one is gonna be, let's see where's iron. I need to get another one. Apologies, guys. Let me stop sharing for a sec. I need to get another periodic table. Apologies, guys. So we're gonna look at the periodic table and then we're gonna look for where's iron. Just bear with me one sec because I need to get another periodic table. Okay, okay. All right. Okay, Jamie said 26. Good job, Jamie. So let's see, let's see. Okay. Apologies, guys. So now I have my periodic table handy. So now I have my periodic table. I'm gonna pull this up, right? And then I'm gonna close this one. This one wasn't helpful. Okay. So I have my periodic table here, and I'm gonna look for iron. And iron's gonna live right here, right? So iron's gonna live right over here. And then the previous one I see is argon, okay? So I know that the previous noble gas is argon, so I don't know how to eliminate this yet. But then I gotta look at what? I gotta look at the S block and the D block, okay? So the S block I see for iron lives right over here. So that's gonna be 4s2, right? I'm gonna say 4s2. And then what about here? 1, 2, 3, 4, 5, 6. Now what is it? Now what is it? Now that we counted 1, 2, 3, 4, 5, 6, is it gonna be 4s2, 3d4, or is it gonna be crying emoji 4s2, 3d6? 4s2 3d4 or 4s2 3d6. Okay, there we go. There we go. Now we're getting some more interaction, right? Right? So when you do it this way, guys, when you have a periodic table, it's not so bad, right? I feel like a lot of people didn't know at first, but then once we have the periodic table, all I do is simply look at the previous noble gas and I count 1, 2, 3, 4, 5, 6, because that's going to be in the D block, right? Let me know if there's any questions there. Let me know if there's any questions there, because I think people are a little bit scared for electron configuration, and then if you break it down, it's not always too bad. Okay, let me know if there's any questions there. Good, good. We're feeling good about this one. How does the F block work? F block works the same exact way, okay, except The only catch, okay, I forgot to mention, the only catch is for the D block. Notice that it's in the fourth row, but for the D block, we subtract one. So if we're in the fourth row, we have to subtract one for the D block. Okay? All right. And then if we're in the fifth row, we got to subtract one for the, we got to subtract um another one for the D block. So if we're in the fifth row, we're going to be in the 4s, we're going to be in the 4d orbital. Now, someone said, how does the F block work? We're going to skip we're going to subtract by 2. Okay, we're going to subtract by 2. So in a moment, we're going to do an example with the F block. That's so much easier than what I've been doing. Literally do the whole configuration, then go to the condensed one. That's right. Yeah, that's right. You can do the whole configuration, but that's going to take a lot of time. Okay? It's going to take a lot of time. So in a moment, we're going to do the F block. In a moment, we're going to do the F block. I just want to go over electron filling. So does everyone see? So you have the slides here, and I want everyone to see this picture on the right. Okay, this picture on the right is going to indicate your energy levels. So someone said, so Jamie said, I start from the beginning. I start from the bottom. 1s2, 2s2, 2p6, 3s2, 3p. So I don't want you to memorize this, chat. Don't memorize this. This is going to be your formula, but don't memorize this. I want you to practice. So we're going to go over the F block in a second. I just want to see where that is. Yeah, here we go. This one has the F block. Okay, but also Hund's rule. So does everyone understand Hund's rule? So someone comment down below. How do we do Hund's rule? Okay, so to do Hund's rule, we have to do the electronic configuration. So suppose I want to do beryllium. So beryllium is going to be the fourth element. So I got to do helium here. And then I got to add 2 more electrons. Helium, 2s2. So in total, I have 1s2 and 2s2. So I have 2 electrons. Okay, so I'm going to go down and then up and then down and then up. Okay, and then similarly for boron, I'm going to have 1s2, 2s2, 2p1, right? I'm going to go 1s2, 2s2, 2p1. So that's going to be helium, 2s2, 2p1. So now I'm going to go down and then up and then down and then up and then down. But now I'm at carbon. So what does Hund's rule tell me for carbon? So someone comment down below, what's going to happen here for carbon? So I'm going to do a wrong example. Someone tell me why this is wrong. I'm going to do 1s2, 2s2, 2p2, and then helium, 2s2, 2p2. So I'm going to go down, up, down, up, down, up, right? Right? So what's wrong here? Why is this wrong? Why does Hans rule tell us this is wrong? Brandon says it's like you fill all the boxes with one before you put another one in, right? Exactly. Brandon, what Brandon said is correct. Hans rule says we have to kind of build it one at a time before doubling it up. Okay? We're gonna build it one at a time before doubling it up. So we gotta do not one, two, we gotta go down and then up, up, just like that. Okay? 2 up arrows. Okay? There you go. On 4, electrons are filled singularly before pairing. Good, good, right? Right? Good. So let's see some thumbs up, guys. So let's see some thumbs ups if that's making sense for Hund's rule. So let's see some thumbs ups if we have one for Hund's rule. Okay, there we go. Kayla understands that. Brandon, Casey, Betsy, thank you, thank you. Okay, so everyone's getting that. We're gonna skip over Hund's rule. So if you don't understand Hund's rule, I want you to fill out every single one of these and then do that for practice. So let's skip over because it's already 6:20. I want to get to resonance, guys. I want to get to resonance. Okay. Okay. So another quick one, guys. Which of the following is going to correspond to lead? So everyone get out your periodic tables and then let me know which one it is for lead. So I'm going to zoom into my periodic table. So if you think it's going to be 6s2, 6p2 for lead, you're going to vote for a happy face emoji. If you think it's crying, then you think it's this one. So what do you think it's going to be? What do you think it's going to be for lead? And see, I don't even need my periodic table. I don't even need my periodic table for this one. I'm going to delete this. I'm going to delete this. There we go. Elizabeth says crying, Ready crying, Brandon crying. Good job, good job. Good job, right? Right? Because this is violating Hund's rule. We have a double electron here. Violates Hund's rule, right? Right? So it's not going to be happy face, it's going to be crying emoji, right? Okay. Okay. Everyone seems to be getting that. Everyone seems to be getting that. So we're going to quickly go over. I think we're going to skip this one too. We're gonna skip this one because I think everyone seems to be getting that. I want to get to electrons. Um, atomic sizes as well. We're gonna skip this, but read about this if you haven't already. Make sure you read about this. Ionization energy, please, please, please read about this. This is really important. So I'm gonna skip that. I'm gonna skip that. All right, all right. We're gonna be done with chapter 3. So any more questions about chapter 3 before we any more questions about chapter 3 before we move on to chapter 4? All right. Brandon has a question. Do you want to just unmute yourself? If not, it's fine. If you want to just type it, it's fine. If you want to unmute yourself, you can unmute yourself. All right, all right. Oh, and apologies, I skipped over the F block. Let me go back to the F block real quick. I skipped over the F block. So the F block that someone said, how does the F block work? So we subtract by 2. Okay, we subtract by 2. So once I get to the F block, we subtract by 2. Okay. So what do I mean by that? So maybe we better do this one more example and then we'll be done. Okay, so suppose we want to do the electron configuration for lead. Okay, suppose I want to do the electron configuration for lead. I want to go to my F block now because lead goes all the way to the bottom here. So I'm going to look for lead and it's all the way on the bottom here. So notice how I have to pass the F block. Okay, so if I want to go to this block, this is my 6th row. But then this is my F block. So I'm not going to say 6F. I'm going to subtract by 2. I'm going to say 4F. Okay? Does everyone understand what I mean by subtract by 2? So I'm going to go to my 6S2. So I'm going to say it's my 6S2 and then 4F. Okay? 6 minus 2 equals 4. So that's why it's 4F. Okay? So that's why all of these that have 4F are potential candidates. So I'm going to ignore anything that has 5D here. Okay? And then in my F block, I have to count how many electrons I have. I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. I think I miscounted, but I believe it should be 14. So if I fill the full valence shell, I'm going to have 4F14. So notice all of these have 4F14. So I have 7 boxes here. 7 times 2 electrons each is 14. So 7 boxes times 2 electrons is 14. Okay? So that's why all of these are F12. Okay, you guys are asking the exact same question. So if you take away 4 electrons to make a cation, which block do you take electrons from? So which block do you take electrons from? The one on the all the way to the end. All the way to the right. Take away here. The analogy I like to say, take away here at the end. The analogy I like to say is you want to take away the low-hanging fruit. If you're hungry and you want to grab a fruit from a tree, you're not going to go all the way to the top of the tree and then climb the top of the tree and then pick the top. No, you're going to go for that low-hanging fruit, right? So all of this stuff is low-hanging fruit. Okay? This is stuff on the right-hand side. You're not gonna pick the stuff on the left-hand side here because that's all the way at the top of the tree. Okay? So you take away from the highest quantum number. Not the highest quantum number, you want to take away from the one in this, okay? In this figure. So do you see how all of these are in order? This figure is key to understanding here. Notice that 1s is at the this is the hardest one to take. This is like getting the fruit from the top of the tree. Okay? It's not always the highest quantum number, it's whatever has the least ionization energy. Is the least ionization energy. This is a really common question people ask me. Okay? So this is the low-hanging fruit. Anything at the top here. Low-hanging fruit. Does that make sense? Does that make sense? Okay. Okay. So let's see some more thumbs ups if we're done with chapter 3. Like quick crash course of chapter 3. That was like 20 minutes of chapter 3. So let's see some thumbs up if we're done with chapter 3. We want to do Lewis structures and resonance. Okay, thank you, Betsy, Elizabeth. All right, appreciate y'all. All right. So like I said, that was a quick crash course. We still have more practice problems. I want you to read on atomic size. I want you to read on ionization energy, and I want you to try some of those practice problems. We're gonna be done with chapter 3 because everyone's asking more about chapter 4 and 5. All right? All right, we're gonna move on to chapter 4 and 5. So what is the overall trend for electronegativity on the periodic table? Is it gonna be happy face up and to the right or crying emoji down to the left? So what is the overall trend for electronegativity on the periodic table? Is it up and to the right or is it down and to the left? Okay. Okay, good. Caleb got happy face, Rediot, happy, Tran, happy. Okay, Brandon, so I know fluorine is the highest. So that is correct. If fluorine is the highest, then what does that mean? Okay, what does that mean? It means that our trend, anything that is to the right-hand side is more electronegative, right? Anything on the right-hand side, for instance, fluorine, because Brandon said, all right, I know fluorine is the most electronegative, but poor francium is not electronegative. So the trend is horizontally to the right and vertically upwards. So in total, the trend is up and to the right. Okay, so if you said up and to the right, good job. Right? Right? So that's kind of the end of chapter 3 and into the beginning of chapter 4. I noticed he didn't do a lot of practice problems for this equation, but we're going to skip that for now. But I want you to read up on that equation too. And then he didn't talk much about this diagram, but this is also a common test question. So this is the equilibrium bond distance. Notice that we have the lowest energy here. So we're going to skip over this, but again, please read about that, okay? Read about that. We don't have time to go over every single detail. So we're going to skip that. We're going to skip that. Okay, you have the slides and you can read about it. All right. So naming compounds and writing formulas. So the first word of the name in the first is the name of the first element in the formula, and then for the second word you change the ending to IDE. Okay, so you have to memorize your prefixes, right? So this is just straight line. You have to memorize. One is mono, right? Two is di, three is tri. Okay, so you basically have to memorize that chat, and then you're gonna have to go through and then um yeah, basically memorize each of those different rules. Okay, so then we're going to go down here and then so based on that, what is the correct name for SO2? Sulfur dioxide or monosulfur dioxide? The slides are in the chat right now on Zoom. The slides are here in the Zoom chat right here. Just scroll up to the Zoom chat. Okay, so sulfur dioxide. Okay, good. Okay, so So no one fell for this trap, okay? So no one fell for this trap. So he's gonna try to trick you and he's gonna say, wait, what about mono? I just told you that if I have one sulfur here, then I'm gonna say mono, okay? So that's a trap. The reason it's not monosulfur dioxide and it's sulfur dioxide is because you don't use it for the first element, okay? So that's a very common trap, okay? So a lot of people get confused with the first element. They say it's monosulfur dioxide. No, for the first element, we don't care. Okay, good. So then for ionic compounds, the first word is the name of the cation, and then the second word is the name of the anion, and then again, you change that to IDE. So again, we're going to skip over these, but I want you to try these out. Um, and then yeah, so but just real quick, you can try those out for instance, potassium bromide. I want you to memorize these ones. Calcium oxide, okay? And then you have the charges as well. So please read about that. The slides are here in the Zoom chat. All right, next is binary ionic compounds. So what is the correct name for NiS? Is it nickel 1 sulfide or nickel 2 sulfide? Is it nickel 1 sulfide or nickel 2 sulfide? All right. So how do we do this, chat? So I'm going to check my periodic table. I'm going to check my periodic table. Okay. So how do I answer this? So I'm going to go to my sulfur. I'm going to go to my sulfur here, and then my sulfur has a charge of what? My sulfur has a charge of, Liz, right here is going to be -2, right? So sulfur has a charge of -2. Nickel, I'm not sure yet. Okay, nickel, I'm not sure yet. So I need to be careful. I need to be careful, and I need to write my sulfur is -2, my nickel is -1, and then I notice they combine to form NiS. So if they combine to form NiS, that means we're gonna do this crisscross method. So this is gonna be Drew's crisscross method. So the crisscross method means I'm gonna take my number that's up here And then I'm gonna take my number that's over here. I don't know what this is yet. Okay. And then I'm gonna do crisscross. So I'm gonna say for my first step, this is my Ni2, and you take the absolute value of it. So the absolute value of -2 is +2. So I'm gonna say Ni2 S question mark. Okay. But I know that my final answer is NIS. So I have to take the least common denominator, which has to be 2. Which has to be 2. So in other words, if I take the least common denominator, and I know that for Ni is 1 and S is 1, that means that my final answer tells us that this came from a +2 nickel ion. So the correct answer is nickel 2. Okay, I know that's a little bit confusing, but try the crisscross method. Let me know if that made sense. Okay, if that made sense, put a thumbs up. If that didn't make sense, put a crying emoji. Thank you, Kayla. If that made sense, put a thumbs up. If that didn't make sense, put a crying emoji. Okay, cool, cool, cool. So use the crisscross method only works. The crisscross method only works for ionic compounds. It does not and metallic compounds. It does not work for covalent compounds. The crisscross method only works for metallic compounds. So once you see I have a metal, and the reason I know it's a transition metal is because it lives right over here. This is again the D block. Remember when I asked that first question? It was for the D block. Okay, that's going to be a transition metal. Would you not use it for the S block? We can also use it for the S block. Yes, we can use it for the S block because these are still metals. Okay. How did you get the -2? The -2 is for my sulfur. So anything that's in this column is going to be -2. So this is my column. This is sulfur and oxygen. This is -2. This column is my halogen. This is -1. Okay. And then this is +0. So you just memorize +0, -1, -2. Okay, and then for nitrogen, carbon, we'll talk about these. Okay? Okay? So I know we're going really fast, guys. It's already 6:30. I want to get to Lewis structures. Because pretty much the rest of it is going to be Lewis structures. Okay, and we're almost there. All right, we're almost there. Now we're at polyatomic ions. So I would say if there's one table that's the most important for everyone to memorize out of the entire exam, out of the entire, maybe the class, is this table right here. Like, it's a small table, but I cannot emphasize this is so important, okay? A lot of the times people struggling with OChem C, I mean Gen Chem C, is because they just simply forgot their polyatomic ions, okay? So we're gonna try our best to basically memorize as many as we can today. So now it's 6:30. So now 6:30, we're gonna do our best to do as many as we can. Um, are there any particular ions that people like want to jump into right now that they're like, hey, I need this one right now. Okay, I need this one right now. Brandon says I figured out how to remember them. Okay. So for instance, for instance, like, do you guys understand the rule? If we have ClO minus, okay, versus ClO4 minus. If you have, so someone tell me what's the rule here. If I have, for instance, 3 oxygens here, and then a minus charge, that's going to be called chlorate, right? And then if I have 2 minus here, then that's going to be called chlorite here. But then what's the rule if I want to add one more oxygen? So if I want to go from 3 to 4, what's the rule? Or if I want to go from 2 to 3, what's the rule? So chlorate, I have to pretty much memorize that. That's just going to be ClO3 minus. And then chlorite, I pretty much have to memorize that. So 3 is more than 2, so that's 8 versus 8. But if I want to add one more oxygen, that's going to be ClO4 minus. That's going to be called perchlorate. Perchlorate means +1. I'm going to add 1, ClO4 minus, right? And if I want to subtract one oxygen, I'm going to take away 1. That's going to be hypo. Okay, so like think like hyper, like you're hyper, you have more energy. So kind of the same thing. So per means more. Hypo means you have less. So hypo means you have one less. Per means you have one more. Right? Is everyone good with that one so far? Are we so far so good with that one? Okay. So that's gonna be chlorate, chloride, perchlorate, perchlorates. So the rest of them, we're gonna just build them one at a time. Okay, we're gonna just build them one at a time. So we're gonna do a combination of chapter 4 and 5, also acids in a second. So again, last minute chances for chapter 3 questions, and then the rest of it we're gonna do pretty much just Lewis structures and molecular geometry. Let's see some thumbs ups. If that's a good idea, pretty much for the rest of it, we're gonna do a bunch of examples. If that's a good idea, let's see some thumbs up. Okay. Yeah. Yeah. Let's do as many as we possibly can, chat. Let's do as many as we possibly can. So we have the strong acids here. I also want you to memorize them. I was trying to find a really good mnemonic. I wish I can tell you it's gonna be really bad, but it was something like this. It was like, hi, um, class. It was hi, class is boring. No. Something like that. That's all I can remember. It was hi, class is boring, and then call me later, something like that. Okay. So you can memorize perchloric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, and sulfuric acid. So all the acids have what in common? All the strong acids have what? What do all the acids have in common? Yeah, exactly, right? So they're going to donate this proton here. So acids are going to be proton donors. Sulfuric acid is the only one that is diprotic. Di meaning two, protic means that it's going to be donating two. So sulfuric acid is going to be H2SO4. So di means two. Di equals two. Okay? So good. All right. And then, yeah. Lewis structures and molecular and ionic and electronic geometry. We're gonna try to combine chapter 4 and 5 into one. Okay, we're gonna try to combine chapter 4 and 5 into one. So we're gonna start with the Lewis structures and we're gonna start with the electron geometry versus the molecular geometry. Okay. So you have this table here. Pretty much, please, everyone memorize the table. And then, yeah, we're gonna try to do as many as we can today in the next 90 minutes. Okay. So the first one, we're gonna start off easy, and then for the rest of it, just let me know which ones you guys want to do. So I'm gonna start off with methane. So what's the formula for methane? So what's the formula for methane? I know it's gonna be CH4, right? So some of you are really good at this already. Some of you need to like have some good study strategies. So how do I know? I'm gonna do it the long way right now, and then after this one, we're gonna do it the easy way. So the long way is I have to start with step one is determine the center atom. Okay, so how do I know what's the center atom? And then sometimes people say like, how do you know? How do you know? I don't know, I'm gonna guess. Okay, so I'm gonna just guess and say that carbon is the center atom, right? Okay. So I'm gonna just take a guess, and then how many valence electrons do I have to add? So step two is add valence electrons. I forgot to also say step one. Let's make that step, pardon guys, let's make that step 2 and 3. Pardon everyone. This is gonna be step two. Let's do step one is calculate the total number of electrons. Calculate total number of electrons. So how many electrons do I have for carbon? So carbon, valence electrons, not electrons. We're going to do valence electrons. Valence electrons. So carbon's going to have how many? And then H is going to have how many? Okay. So carbon, good, right? Carbon's going to have four. And then we have 1 times 4 because we have 4 H's. So in total, that's going to be 8, right? Right? Chat, comment a thumbs up if you're understanding valence electrons so far. Okay, comment a thumbs up if you understand valence electrons. Okay, so then next is determine the center atom, which we're gonna guess is carbon, and then we're gonna add 4 valence electrons. So I have 1, 2, 3, 4. Okay, then I hope you understand that we do 1, 2, 3, 4. Okay, so that's how we build methane, and we fill the rest through the bonds. Then we're gonna do step 4 and 5 and 6, which is to do resonance and this and that, but we're gonna start easy. So comment a thumbs up if methane is easy. Comment a thumbs up if you understand methane. This is CH4. Okay. Now this is chapter 4 CH4, but what's wrong with chapter 4 CH4 versus chapter 5 CH4? So namely, why is this current structure wrong? Why is this current structure wrong? How do I determine the molecular geometry versus the electronic geometry. So what is the molecular and what is the electronic? So what's the difference? So molecular means I count what? I count how many atoms, right? Molecular versus electronic. So I need to look at the steric number. So the steric number is going to tell me how many lines do I have in total. So I have one, two, three, four electron groups. So I have four electron groups. So my steric number is going to be four. Okay. So I can either memorize the table or visualize. We're going to do both. If you like to memorize, I like to visualize. Sometimes people like to memorize, sometimes people like to visualize. So if people like to memorize, you're going to go to the table and memorize. If the steric number is 4, that is called tetrahedral. Okay? If you like to memorize, you go to the table, steric number 4, tetrahedral. I don't like to memorize. I'm going to draw it. I'm going to visualize. So I'm going to draw a structure with carbon in the center and then a 3D structure. Okay, because methane is not 2D planar, it is 3D. So now I have this carbon looking figure with a 1, 2, 3, 4, right? And then I have this shape. The name of this shape is a sort of pyramidal kind of shape. This is called tetrahedral. Tetrahedral. So if you like to visualize, visualize what that shape is. If you don't like to visualize, don't worry, you can memorize the table. Hang on, is the most commonly referred to as molecular versus electronic because I've been referring to as molecular geometry and molecular shape. Oh, that's a really good question. Oh, that's a really good question. What's molecular shape? Let's see what the table says. The table says molecular geometry. Yes. The table says molecular geometry, and then they call it electron pair geometry. Electron pair versus molecular geometry. So you need the key word is molecular versus electronic. No, you're missing the word electronic, Brandon. It's not molecular shape versus geometry. It's electronic versus molecular. Dave says it as shape. So I say molecular geometry. Okay, let's change that to molecular shape. Molecular shape and electron pair shape. That's fine. Okay, so I'm gonna say geometry, you're gonna say shape. Okay? Okay? Okay. So, but in this case, the electronic is the same as the molecular. So they're both going to be tetrahedral. And we're going to do an example of when they're different. So in this case, they're the same. So for both electronic and molecular are going to be tetrahedral, right? Good, good. Are we good for methane? Good. Are we ready for some harder ones? Good. Thank you, Kayla. Thank you, Brandon. Okay, good, good. And then let me know, drop a crying emoji if you're stuck. Okay, if there's one molecule that's like the most important molecule of all time, is going to be water. So water is going to be H2O. So how do we draw H2O? So now this is where I want you to start kind of skipping steps. So instead of doing like the like electrons, like yeah, we're gonna have, 6 plus 2 electrons, we're gonna have 8 valence electrons. I want you to kind of start skipping steps. I know that oxygen is going to be singly bonded to water. And then how many lone pairs am I going to have, chat? How many lone pairs am I going to have here? How many lone pairs? Okay, two. Two lone pairs. So I'm going to have two lone pairs. Okay. Why did I curve them down? Why did I put H on an angle like this and not straight across? So why did I put my single pair like that? Okay, Brandon said bent. Okay, very good. So I'm going to draw my little bubbles because remember in chapter 3 we said that electrons are bubbles. So electrons are represented by these bubbles and they cause electron repulsion here. So that's why it's called VSEPR, electron repulsion theory. Okay, so now H is repelled. Quick question, has he talked about polarity versus like dipole and like dipole moments? Has he talked about, do you need to know something is polar and nonpolar or not yet? And if you need to know, let me know if this is polar or non-polar. Okay. We need to know polar versus non-polar. Okay. So how do you know something's polar versus non-polar? So people are like, oh, if oxygen, people are like, oh, if something has oxygen, it's polar. No, that's not always true. Okay, that's not always true. Just because it has oxygen doesn't mean it's polar. Okay, in this case though, let's see what happens. So we have some electron density here, and then I'm gonna put some negative charges here. This symbol is called partial negative. So if on this side I have partial negative, that means I'm creating a dipole moment because oxygen is electronegative. So if this side is electronegative, what does that make this side? What does that make this side? If this side is electronegative, then this side is going to be electropositive, partial positive, okay? So that's the definition of polarity. Polarity does not mean I have an oxygen here. Yes, I do have an oxygen here, but oxygen does not mean polarity. Polarity means that I have a charge difference, namely I have kind of like a magnet. Do you see how this is almost like a magnet chat where I have the half side split in the middle? This is the negative side, this is like the North Pole, and this is the South Pole, okay? So polarity means I have almost like a magnet here where I have my polarity here, okay? Does polarity mean H plus and OH minus? No. Polarity does not mean H plus versus OH minus. It means that I have a charge difference on one side of the molecule and the other. So if someone said, "Are you sure it's not on the test?" Someone said it's not on the test, so we're not going to worry about it too much. Someone says it's not on the test, so we're not going to worry about it too much. So, so now I have my water molecule, and I'm going to do 1, 2, 3, 4, 5, 6. Now my question is, what is the electronic shape and what is the molecular shape? So, So for the let's do the molecular shape because someone already said bent. So it's pretty clear that I have this kind of shape here. So I'm gonna highlight this, right? I'm gonna highlight this as my this is my molecular shape here. So if I have my molecular shape, I gotta count the steric number. So what's the steric number? It's gonna be the electron groups. So that's gonna be one bond here, two bonds, three, four. Notice how my lone pair is one group here. Okay. Notice how I have my one, two, three, four. That's four different groups. So my steric number is gonna be four. If my steric number is four, then I'm going to look at how many atoms I have, and I have two atoms attached to H. So if my steric number is 4 and I have two atoms, that is called bent. Okay, that is called bent. So if you don't like visualizing it, then you're gonna memorize the table. So I go to Sn equals 4, and then I see I only have two lone pairs with two atoms. That's called bent. So the example they give here is right here. That's water. H2O is bent. Bent means it looks like a boomerang. Now Casey says tetrahedral. Good. So if my steric number is 4, that's my electronic geometry. So my electronic geometry, now I gotta redraw that one more time. I'm gonna draw a little funky chat. I'm gonna draw it like this. I'm gonna put my oxygen down here and then my water over here. And then one lone pair I'm gonna put up like that, and the other one I'm gonna look like that. Wait a second, that one looks familiar. That one looks like the pyramid shape that Drew drew a second ago. And that looks like my pyramid shape. That's why the molecular is bent, but the electronic one is tetrahedral, right? Right? So I have different electronic configuration. I have two different shapes here. My electronic configuration is tetrahedral versus my molecular is bent. Let me know if, yeah, let's see some thumbs up. Did that make sense? Did that clarify things or did that make it more confusing or that people like already got that? All right, lots of thumbs ups, lots of thumbs ups. Thank you, Brandon. Thank you, Rhetoric. Right? Okay. Any questions about water? Any questions about water? Because this one is like super important. This one's like super important. Any questions about water before we move on? And then I want to do some resonance too, guys. Don't worry, we're gonna do resonance. All right. All right. I'm not seeing any questions about water. Is benzene polar and why? Benzene is non-polar, and that's going to be in a slightly different scope on before because that's going to be in the context of organic chemistry. Benzene is going to be non-polar because we just have um, only double bonds. Okay, only double bonds. There's not going to be any electronic charge difference. I think it's like if the shape doesn't match the geometry, then it's polar, with the exception of square planar. Hmm. I don't know about that. If that could work. That could work. I'm not sure. We're gonna see if that's true or untrue. Okay. How would you draw it in the 3D shape with dark wedge and dashed lines? Um, um, yeah, not for water. Not for water. Water is not gonna have wedge versus dash. Water is only gonna have, this is how you would draw it in 3D. This is how you draw it in 3D. Okay. With the dark wedge and the dashed lines, even that's gonna be only for your organic compounds. Okay. Brandon brought up a good point. I'm not sure about that. Like we're gonna see if that's true. Brandon says if the geometry is different than the molecular geometry, that if the shape doesn't match, then it's cold. Okay. Okay, and then all right, guys. So we're gonna move on from water. Let me know if there's any more questions. Carbon dioxide. Like, does anyone really want? I kind of want to skip some of these, so I'm gonna skip around. So this is gonna be your homework. This is gonna be your homework. So do the same thing for CO2. I want to skip CO2. Let me know if there's any. Um, Let me know if there's any. Quite like someone really wants to do CO2. Okay, N2HF. All right, N2HF. So let's do that. So we're gonna do N2HF. So N2. Oh no, NH2F. NH2F. Okay. All right. So we're going to repeat that process. We're going to repeat that process for N2HF. So everyone comment down below how many total electrons we have. Comment down below what is the center atom, and then drop a screenshot of your picture of what the Lewis structure looked like. And then you're going to tell me what is the molecular geometry and the electronic geometry, okay? And let me know if there's resonance, which we haven't talked about resonance yet, but we have a lot to go over for this particular compound. So I'm going to get started with you. So nitrogen has 5 electrons, hydrogen has 1 times 2, and then fluorine has 7 electrons. So 5 plus 2 is 7, plus 7 is 14. Okay? So 14 valence electrons. Okay? We're going to have 14 valence electrons, and then we're going to do nitrogen as the center atom. And then I'm just going to just guess. What if I just guess that nitrogen here is H here, and then F? I'm gonna have 1, 2, 3, 4, 5, 6, 7. I'm gonna have a lone pair just like that. Okay, so what do I see here? So I see that, first of all, is my octet complete? 2, 4, 6, 8. Yep. I don't have any charges here because fluorine has 7 valence electrons, and then I have 1 single bond. So now my Lewis structure is complete. So I know I'm going really, really fast. Okay, but if you want to build it from scratch, follow the rules. Step 1, build the center atom, count the valence electrons. Let's just double check. I have 2, 4, 6, 8, 10, 12, 14 valence electrons. So now I know I'm done. I have no charges here. Now we're going to do the electronic configuration and the molecular geometry. I mean the molecular geometry and the electronic geometry. So some of you like to see it visually. I'm visual and some of you want to memorize. So if you want to memorize, we got to do the steric number. So what's the steric number? The steric number is going to be how many electron groups do we have? So how many electron groups do we have here, chat? How many electron groups do I have on nitrogen, hydrogen, fluorine, and H? Okay, so I see I have 1, 2, 3, 4. So I have 4 electron groups. Okay, so that means that my electronic configuration is going to be tetrahedral. So if my electronic one is tetrahedral, that means I have this pyramid shape. Oh, okay, now I can visualize. Now I can see, right? That's going to be my tetrahedral, right? Let me know if that was too fast. Was that too fast? What's the last step? I gotta look at my electronic. So this was my electronic one. Now I gotta look at my molecular. I gotta look at my molecular configuration. So I see that now for my molecular, I'm not gonna consider my electrons. I'm gonna erase that. And my pyramid is now looking like this kind of funky pyramid. So this is like a trigonal, what is that called? I forgot the name of that, chat. What's the name of that pyramid shape? Trigonal pyramidal. Okay, so that's gonna be a trigonal pyramidal kind of funky shape. So see what I mean, chat? The electronic is tetrahedral, but the molecular is trigonal pyramidal, right? Right? So let me know if that was too fast, okay? So drop a thumbs up if you follow along with that one. That was a good one. That was an easy one. And then drop a thumbs down if that was too hard, that was too fast. I got confused. Okay, I've got some thumbs up. Got some thumbs up. Okay, good. No one got lost there? Okay, good. Y'all are crushing it. Good job. Y'all are crushing it. So yeah, chat. We have all these examples. So pretty much the floor is yours, guys. The floor is yours. We have all these examples. We have ammonia, ozone, peroxide, sulfate, sulfite, nitrate. I think the next one I'm going to do is nitrate, okay? We're going to do nitrate. You have perchlorate, chlorate, chlorite. And then we have all these practice problems, okay? So let's do nitrate next because we haven't talked about resonance, but look how many there are here. Some of these are from the book, some of them are from like my own. So we're going to do as many as we can. So for example, this one here, nitrate. Okay. Who wants to do nitrate next? Comment a thumbs up if you want to do nitrate next. Okay, so let's do nitrate. All right. So nitrate, he might be nice and he might say nitrate NO3 minus, or he might be mean and he might just say nitrate, no formula. So that's why you have to memorize that table. Okay, remember you have to memorize that table. This is a polyatomic ion. So the person that said, "Hey, I'm confused about Lewis structures for multiple atoms," you have to memorize your polyatomic ions. Okay, so NO3 minus. Okay. And then, so same exact thing, chat. So we're going to repeat that process. How many total electrons? How many total electrons? So nitrogen has how many? And then oxygen has how many? So how many total electrons are we going to have? So I know nitrogen has 5. And then oxygen has 8. So I have 5 plus 3 times, excuse me, 6. That. And then I have a minus 1. Okay. Plus 1. Okay, whenever you see a minus charge, you have to add 1 electron. Okay, good. So we have 24 in total. 24 in total electrons, right? So let's see some thumbs up if we agree that nitrate has 24 total valence electrons. 5 plus 3 times 6 plus 1. Okay, good. Good. So we have 24 total valence electrons. Now, I have to make a guess. If I had to guess what's going to be the center atom. So some of you already memorized this one. So if you had to guess what's going to be my center atom, it's got to be nitrogen, right? It's got to be nitrogen. So I have to make another guess. Do I want to put my nitrogen next to like multiple oxygens, or do I want to like, I don't know yet. So I'm going to just guess and I'm going to put oxygen just like that. Okay. So now I have to do, so here, notice how I already put single bonds. So I skipped the step where you do the valence electrons and the octet rule. I skipped that step because I want to be smart because I don't have enough time. On the exam, we don't have time to do the whole step by step. So I know that at the end of the day, I'm going to put a minus charge right here. So on the exam, I don't have enough time. So I'm going to start filling in my electrons here. I know nitrogen is going to have 8 electrons in the center, and I have to be careful with my exceptions. Single pair of electrons. 1, 2, 3, 2, 4, 6. All right. Now the next thing we haven't talked about is formal charge. So formal charge has a formula, and then I'm going to give it my closest definition to the one that he did. So the one that I do, I say that it's the number of valence electrons minus the dots plus lines. This is the way I like to tell people the formula. I think he said it's like the group number, or like the column. It's like the column minus the electrons. Okay, valence minus dots minus sticks. There you go. I like that. So he said valence minus dots minus sticks, right? Same formula. I'm going to say my formula, guys, okay? I'm going to say my formula, which is the valence electrons minus dots plus lines. And we have to be quick with it. We have to do that for every single atom. So I'm going to start with nitrogen here. And so how many valence electrons does nitrogen have? I'm going to be quick with it. It typically has 5. So I'm going to put a 5 right here. And then now I see how many dots. I see 2 dots minus 2 dots plus 3 bonds. What do I mean by lines? I mean these bonds. So 2 plus 3, okay? So 5 minus 2 plus 3, that's 5 minus 5, so I'm going to put a plus 0. All right. I'm going to repeat that process for oxygen. So oxygen is going to be 6 minus how many dots? 1, 2, 3, 4, 5, 6 minus plus 1 line, okay? So 6 minus 6 plus 1, that's 6 minus 7. And then 6 minus 7 is minus 1. So I'm going to put a minus charge right over here. Why is there a lone pair? Because I'm still building out my Lewis structure, okay? And the lone pair here is because I have 2, 4, 6, 8 total electrons, okay? And then on this side, I have same thing here. So I'm going to repeat that process. I'm going to say I have a minus charge here and a minus charge here, okay? So that's going to be my total electron here, my valence structure here. But what's the problem here? Let's see how many total electrons I have for nitrate. So I have 24 electrons, right? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So what's the problem? I have too many electrons, right? Okay, so the problem is I have too many electrons and I donated an extra pair to my nitrogen, and then Brandon said, why did you do that? So that was, now I know that I had to subtract 2 because I had too many. Okay, now I still have another problem. What's my other problem? I need to turn this into a double bond. Why? Because now my nitrogen is complete, right? My nitrogen is complete. And then now I need to redo the formal charge again. Okay, so if I do it here, I'm gonna have 1, 2, 3, 4, 5, 6 dots plus lines. So 6 minus 6 equals plus 0. But for my nitrogen, I have 5 minus 1, 2, whoops, 5 minus, okay, 1, 2, 3, 4. So 5 minus 4 is plus 1. Okay, now I know that I'm done. Now that I know that I'm done because I have plus minus 1 minus 1. Okay, overall, what is minus 2 plus 1? So minus 2 plus 1 is a minus 1. So now I know that I'm done with my first nitrate. Okay, and that's just my first resonance structure. So let me know if there's any questions here with my first nitrate. That's just one nitrate. Can you explain why there's a double bond? The reason there's a double bond is because before I had this, right? Before I had this, but I had a couple problems here. When I had this, I had 2 problems. The reason I know I have a double bond is because I have a single bond, lone pair, lone pair, lone pair. So the first problem is nitrogen doesn't have a complete octet. I have 6 electrons, I need 8. Okay? So that's the first problem. The second problem is in this current state, I have 3 minus, okay? I have 3 minus charge. So I have 1, 2, 3. I don't want a minus 3. I want a minus 1. So the minus 1 up on top here indicates my total charge for my overall structure. So that's why I had to have a double bond, okay? So that's my first structure. What do I got to do after this, chat? What's my next step? Right? What's my next step? I know I'm done with one structure, but I'm gonna have what? What is the name of the next step that I'm doing here, chat? So I'm gonna do this one and then this one. Exactly, resonance. So sometimes people like ask me like, how do you know? How do you know if there's resonance? Okay, I don't know. I don't know because I've never seen this molecule before, but I'm gonna try it out. So resonance, does everyone understand the concept of resonance? Comment down below. Let's see if put a thumbs up if you know the resonance, and then put a thumbs down if you have no idea what is resonance. Okay, Brandon said honestly not really, that's fine. All right. And then some people said yes, some people not so much. Okay, so resonance, I can't, some of you be jumping to resonance after I already, some of you trying to be doing resonance before finishing your Lewis structure. You can't do resonance until you finish your Lewis structure, okay? So Lewis structure first and then resonance. So this is one Lewis structure, okay? So don't do resonance until you're done with Lewis structure. Resonance is the last step you do. Resonance, all I gotta do is where are my electrons likely to move? Okay, and then this is hard for some students the first time, but you have to be knowledgeable with your chapter 3 logic and think, where is an atom hungry for electrons? Where is an atom hungry for electrons? So I know that this oxygen is hungry for electrons, right, Chad? Because oxygen is electronegative. So maybe willy-nilly, this double bond is going to move upwards. So if I turn a double bond into a lone pair, that means I'm going to turn a double bond into a single bond. Okay, so I'm going to put a nitrogen. My double bond turned into a single bond. Okay, and then now I have these oxygens here. But what's the problem? Because I moved my double bond, what's the problem? What do I gotta fix? What do I gotta fix? Why is this a problem again? Because now my nitrogen does not have a complete octet, right? Right? So now I have a couple options. I can either donate from this oxygen or from this oxygen. I'm going to arbitrarily choose, let's say I choose this one. So every time I do resonance, I'm typically moving 2 arrows. 1 arrow, okay, resonance is 2 arrows. Let's write that down. Let's write that down because hopefully this is going to click for someone. Resonance equals 2 arrows. 1 arrow is a double bond turns into a single bond, and then plus a lone pair. And then another arrow is the opposite. Another arrow, second arrow, is the lone pair turns into a double bond. Okay? So my first double bond turned into a single bond plus another lone pair. And then this single electron pair is going to turn into a double bond. Okay? So now I'm going to flip this too. Okay? So now I'm going to have -1 here, and then -1 here, and then +1 here on this nitrogen. So this is my second Lewis structure. This is my second resonance structure. Good on that one? Thumbs up if we're good on the second one. And then if we're good on the second one, thumbs up, and then let me know what's the third one. Yes, this is different from isomers. Oh, I forgot to bring that. I was thinking about that one for this one. We're going to go back to this one for isomers. Forgot to mention that. This is different from isomers. Um, isomers are not the same thing as Lewis structures. Okay? So if I move one of my double bonds, what do I think I gotta do with my third double bond, chat? What do you think I gotta do for my third Lewis structure? So notice the pattern. Notice that I have a double bond up here and I have a double bond down over here, right? So where do you think I'm gonna have my double bond on the third Lewis structure? So if this was on the top and this one's on the bottom right, where do you think the double bond's gonna live on the third Lewis structure or third resonance? It's gonna live right over here. So this is gonna be a single bond. This one's gonna be a double bond, right? Good job. Good job, Nashon. Okay. So this is gonna be single bond. Okay, double bond. But before we draw that out, we have to draw the 2 arrows. So what a lot of people do, what I used to do is, oh, I'm gonna move over this double bond here and then create a double bond. No, that's not what you're doing. You're not moving the double bond from one side to the other. No, that is not resonance. Resonance means that I'm moving one of my double bonds become a single bond. My other lone pair becomes a double bond. So I need 2 arrows. 2 arrows. Sometimes you can have 1 arrow, sometimes you can have 3 arrows. But oftentimes, this is your rule of thumb. Okay, this is not always the case. You guys know how chemistry always has exceptions? This always has a lot of exceptions too. But often, the rule is going to be this rule, okay? So we're moving one double bond to become a single bond, and then the other single bond to become a double bond. So now I have this, NO3 minus. So nitrate has a total of 3 resonance structures. Make sense? The goal of that's a really good question. The goal of resonance is to stabilize the ion. The goal of resonance is to stabilize the ion. Nitrate is a hard example because all 3 of these are equally stable. We're going to do an example where some ions are not as stable. The general rule of thumb is for resonance, we often have 2 arrows. I know, so I write really fast. Sorry, guys. For resonance, we have 2 arrows. one arrow turns a double bond into a single bond plus a lone pair. And then the second arrow turns a lone pair into a double bond. Okay? I'm gonna write that down and drop it in the Discord. I'm gonna write that down and drop it in the Discord later. So notice how all of this was one arrow, two arrows. This one was a double bond and turned into a single bond. This was a lone pair turned into a double bond. Okay? Any more questions about nitrate? This is like a really, really common test question on like every single chem. I don't know if he's gonna ask about. He likes to do all the hardest ones possible. So I bet you he's not gonna have nitrate. He's gonna have like some harder ones. But if you're not with Dr. Hill, if you're in like a regular Gen Chem class, nitrate is like a super common test question. Okay, so yeah, notice we have three resonance structures. Another thing people ask me is like, how do you know when you're done? How do you know when we're done? It's like, okay, let's try another one. Okay, it's like, maybe I want to try some more. So suppose I tried some more and like, how do you know when you're done? All right, let's pretend I'm not done yet. Okay, I'm gonna move this double bond, turn it into single bond, but then I'm gonna move this one back down and push it down. If I did that, what would happen? So if I move this bond and turn it into single bond and then push this down, well, I got to where I started. Okay? So if you go back to where you started, then you're done. If you got to back to where you started, that means you're done here. So oftentimes resonance is kind of cyclic. So if I wanted to create another resonance structure, then I'm going to go back to where I started. Did that make sense? That makes sense? Let me know if we're good for nitrate. If we're feeling good about nitrate, thumbs up if we're good for nitrate. All right. All right. So would NCO minus be like one of those where resonance helps stabilize the molecule? You kind of read my mind with that one. You kind of read my mind because someone asked me about that one today. So we're gonna do NCO minus. NCO minus. Okay. Okay. So NCO minus, we're gonna repeat the process, but for the sake of time, like repeat the process, da 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 da, da valence electrons, right? I know that one of my structures is gonna look like this. Okay, I'm gonna put carbon in the center, double bond O, and then double bond nitrogen here. I have lone pair, and then I have lone pair, lone pair. Now, I gotta do my formal charge. And then at the end of the day, I want this to be a -1 charge. So my 1, 2, 3, 4, 5, 6. Let's see, is that right? 2, 4, 6, 8. 1, 2, 3, 4, 5, 6. Yeah. So my carbon here is +0. My oxygen here is +0. My nitrogen here is 1, 2, 3, 4, 5, 6. So 6 minus 5 is, 5 minus 6 is -1. So this is one structure. Now I'm going to do resonance. One of them I'm going to move to the left, and the other one I'm going to move to the right. Which one do you want to do first? I'm going to move this one to the left first. Suppose that I move this double bond and turn it into a lone pair, and then I push this double bond and turn it into a triple bond like that. Then what I'm going to have here on the left-hand side is going to be a C N single bond with 1, 2, 3, 4, 5, 6. And then this is going to be a triple bond. Okay, if this is a triple bond, this is going to be oxygen plus, carbon is neutral, and then I have 1, 2, 3, 4, 5, 6, 7. 5 minus 7 is -2. But -2 is really, really bad, chat. If you see -2, that is very rare. -2 is very rare. That's going to be my hint for you, and then we're going to do a pop quiz. So we're going to make this one happy face, and then in a minute, I'm going to ask you crying emoji. Okay? And then let's suppose I go the other way. Let's say that instead of going that way, I went the other way. I went and donated my N lone pair and created a triple bond here and a single bond oxygen. So now I have this resonance structure with a single bond oxygen. This is -1 overall charge. Okay, so I have 3 resonance structures, and I have happy face and crying emoji. This time I want everyone to vote. This time I want everyone to vote. So question of the day is, which one of these is more stable? Is this one more stable? Vote for happy face. If you don't know, just guess. If you don't know, just guess. What's your first thought? This one on the left, happy face, or this one on the right, crying emoji? Okay? So if you think it's crying, happy face, you're gonna say it's this one. Let me write this a little bit better because I know I'm going really fast here. This is gonna be N triple N O minus. Okay, we got a lot for crying. We got a lot for crying. Good, 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 good. So no one said happy. No one wants to say happy. So why is this one not stable? Because I gave it away, right? Because I said -2 is very rare. Why is this one more stable? Someone comment or let me know. Why is that one more stable? Okay, so here's two different things. Charge doesn't match. Brandon got it. Oxygen is more electronegative. So which one is more electronegative, oxygen or nitrogen? Oxygen is more electronegative than nitrogen. So if you understand chapter 3, then it's going to help your understanding for chapter 4 and 5. Again, I'm going to keep saying this. A lot of the times people that struggle with OChem is because they struggle with Chem 1C. And if you're struggling with Chem 1C, it's because you're struggling with Chem 1A. If you're struggling with resonance structures, you're not bad at resonance. You just forgot your chapter 3 logic. So what did we say in the very beginning of chapter 3? We said that anything to the right-hand side is more electronegative, right? So oxygen is more electronegative, meaning does oxygen like electrons or hates electrons? If something is more electronegative, does it like electrons or hate electrons? It's more electronegative. So I like electrons. It likes negativity, right? Nashon says like oxygen is low-key toxic, guys. Oxygen is toxic because it likes negativity. Nitrogen is not toxic. Hates negativity. So if I see oxygen with a minus charge, it's happy. So this one is happy. This one's stable. If I see nitrogen as a -2, that is never going to happen. This is super unstable. It's going to push. So the person that said, hey, what is the purpose of resonance? The purpose of resonance is to achieve a higher stability. Does that make sense? Does that make sense? Let's see some thumbs ups if that clicked for someone. Let me know, like, anyone click? Everyone like, oh, now I get it. Right, right. Okay, okay. Everyone's still saying thumbs up. Everyone's still alive. Everyone's still alive. Okay, okay. Any more questions about this one before moving on? Any more questions about this one before moving on? Okay, okay. So where do we want to go from here? I forgot to mention one thing, chat. Remember when we did this example? I'm going to go back to this example real quick. So that's resonance, but I want to go back to this example because I forgot to talk about isomers. So remember when I put my H to this side and my F down here? That was pretty arbitrary. What if I accidentally, now we're going to talk about isomers. So that was called resonance. Now we're going to talk about isomers. What if I accidentally put my nitrogen like this, and then I put my fluorine up on this side and my nitrogen on this side? Okay. Okay. And then I put my H here and then my H over here. So this is this still possible? Is this still possible? Right? It's still the same structure. This is NH2F, the lone pair. This is still NH2F. So you know that Spider-Man meme when you have Spider-Man pointing at all the different Spider-Mans? That's isomers. Okay? You know the Spider-Man meme? When you have the Spider-Man pointing at all the different Spider-Mans? That's isomers. So this is NH2F and this is NH2F. They just have different configurations, different constitutions. So these are constitutional isomers. Okay, so I didn't do any resonance here. So someone said, is this resonance? No, this is not resonance. This is the rearrangement of the atoms here. Okay, and so you might have two possibilities where one of these, in this case, these are both polar. Okay. Let me think if I remember an example. Let's do another example like this where he might try to trick you. Okay, he might try to trick you. So you might say that this one's polar or non-polar. Okay. So we're gonna do a similar one. Let's see if I remember. So we're gonna do CH2 Cl2. CH2 Cl2. Okay? And then we want to see if this is polar or non-polar. Okay. So if we have CH2, then I know there's going to be tetrahedral because my steric number is 4. So if you're not sure why steric number is 4, repeat that process from the beginning. Count your valence electrons, put your atoms, count the octet rule. So I'm going to put my Cl here, and then I'm going to put my Cl down over here, and then my H and my H. Okay? So this is going to be tetrahedral. Okay? But what if I flip-flop my Cl and my H here? What if I put my carbon Cl over here and then Cl over here and then H over here and H over here? So this is still going to be tetrahedral, but are these isomers? Or are these the same compound? Are these the same or different? That's my question this time, chat. Are these the same compound or isomers? Identical, happy face, crying emoji, isomers. Okay, good. Kayla says isomers. Nash says isomers. Right? Does everyone see that? Because here, these are kind of like on different, right? Different constitutions here. And in this case, they're both going to be also polar. Wait, actually, let's see. Let's see. Are these isomers, chat? Hold on. Hold on a sec. You gotta be careful here. Because if I can rotate then in 3D, I'm starting to think they're identical, chat, because what if I kind of rotate this one in 3D space such that my carbon has my H's out in front. So actually these are actually gonna be, if I'm not mistaken, these are gonna be identical, right? These are gonna be identical. This is technically not cis trans. You're thinking along the right thing, but cis trans is technically a little bit different. Okay? So this is actually going to be identical, right? Because even though they look different, um, I can kind of rotate it. And this is super hard for me to teach, guys. It's so hard for me to teach this because I kind of have to rotate it in my head in 3D. And then I can rotate it and see that those are eventually going to become the same molecule. Okay? Okay? So be really careful. Be really careful when something is identical versus versus an isomer. And then did he talk about cis and trans? Did he talk about cis and trans? Because that's more like an OChem thing. So like cis and trans, maybe he did, huh? So cis is typically going to be for double bonds. So if I have a double bond and then I have X and then X here, I don't think so, but Latia did. Okay, let's talk about just in case. Let's talk about just in case. So if you have cis versus trans, you're gonna have a double bond, and then you're gonna put a line right in your double bond, and you're gonna put a wall. So the double bond is gonna represent a wall. Do you see I have my axis here? That's gonna be a wall. Okay, and then on this side of the wall, these are on the same side. Okay, so this is the wall, and these are gonna be on the same side. Okay, and then on this side, these are on opposite sides of the wall. This is opposite. So on the same side, we're going to call that cis. And if they're on opposite sides, we're going to call that trans. Okay? So that's going to be cis versus trans. Okay? So how we doing, everybody? How we feeling? How we feeling about these? How we feeling about these examples? We have about 30 minutes left. So where do we want to go from here? What do we want to go from here? More examples or any other like questions or homework questions? More examples, more isomers, more resonance, or any questions? Let me know. Let me know. We have more topics to cover. Yeah, we kind of skipped a lot of topics, guys. I didn't go over every topic. I skipped a lot of stuff from chapter 3. I skipped a lot of stuff from chapter 4 as well. Okay? Because there's a lot of stuff to go over. I think one thing we can talk about is acids. Okay, the next thing we talk about next is acids, unless anyone has any questions. I personally prefer, I'd rather you guys have questions because we're still here right now. Okay? If you have any topics you're missing, just read the book. But right now, right here live, I'd rather you have questions. Also have a homework question. Yeah, please. If there's no more questions, we're gonna do acids next, and then just more examples, and then we'll call it. If there's no more questions, we're gonna do acids, couple more examples, and then we'll call it. Homework had a question where it said Cl2O. Yeah, yeah, yeah. I was doing that one too. I was doing that one too. So yeah, yeah, this one, right? Okay, we're gonna do this one next. So what's your question here? I'm gonna go ahead and read the problem and then you let me know what's the question. So chlorine combines with oxygen in several proportions. Dichlorine monoxide, Cl2O, is used in manufacturing bleaching agents. Potassium chlorate is used in oxygen generators aboard aircraft. So we have to draw Cl2O and ClO3 minus, and then Cl is the central atom. Okay. I don't really know what to do. So I looked it up and I was like, O is in the middle. I don't really know why. Okay, so here's why. Here's really simple. Remember when we did H2O? Remember when we did H2O? Look how easy that was. Look, this is like the hacks. H2O was pretty simple, right? Because we just said O was here and then H on the side here, right? And Cl2 looks an awful lot like H2O. So what if I just guess? What if I just guess and pretend it's the same? I don't know if this is right, but so far I'm so good. I have 2, 4, 6, 8, 10, 12, 14, 16, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20 valence electrons. So I have 7 times 2 plus 6. I have 20 valence electrons. So I was right. Like you know what I mean? Like you kind of just guess and then hope for the best. It's not about guessing randomly. It's like being strategic about it. I saw strategically H2O. I know that one's easy. So what if Cl2O looks a lot like H2O? In this case, I was right. Another example like CO2, CO2 does not look like H2O, so that's not always going to work. CO2 does not look like H2O, right? Though it goes against the rule that the least electronegative atom in the middle, but O is more electronegative than Cl. Right, right. So that's why like the octet rule, guys, we haven't done the exceptions. We got to go over the exceptions. The rules can be broken. Octet rule is going to be broken. Electronegativity rule always going to be broken. That's why I'm not a fan of those rules. I'd rather you practice the examples rather than memorize the rules because the rules they never work. They teach them to you, but then they never work, right? Right? So I'm gonna put oxygen in the middle this time, even though yeah, chlorine is more electronegative, but oxygen is gonna be in the middle this time. Okay? All right, should we do the second one, ClO3 minus? Should we do the second one, ClO3 minus? Because we're gonna break the octet rule here. We're gonna break the octet rule here with ClO3 minus. So I'm gonna do Cl in the middle, and then I'm gonna do O3 minus on the side. Okay, and I'm gonna put my lone pair right over here. And then I know I'm gonna have a minus charge as a ClO3 minus. And then I'm gonna put my lone electrons on each of my oxygens. Again, if I'm going too fast, build it from scratch. I also recorded a bunch of these practice problems yesterday. Let me finish up this problem and then I'm gonna plug that real quick. Um, so then I'm gonna have my minus charge here, minus, minus, minus. Okay, but the problem is I have 3 minus. 1, 2, 3. So that means I gotta turn my chlorine here and turn that into a double bond with my oxygen. Okay, so now I have 2, 4, 6, 8, 10. So I'm breaking the octet rule, but I have 1, 2, 3, 4, 5, and then a plus 2 over here. So this one is this one's really, really bad. But this is one possible structure. So this is what the book did. Someone said like, hey, Drew, I think your structure is wrong. But then no, what I did was I did the resonance form. So the resonance was, what if I donate, let's see, what if I donate, um, what I gotta do here? I'm gonna donate this lone pair, kind of like that. I can donate this lone pair. I'm gonna have Cl double bond O, just like that. And then double bond O. Well, I can't do that one here. I forgot exactly what I did, guys. So I did resonance. Let me see if I can pull it up. So I can pull it up right here. I did probably one of these ones here. HClO. I think this one here. Nope. I think this one. ClO3 minus. Here we go. So I said, so the book said that the chlorine was a +2 charge. So this is the book answer, but I didn't like that. I did a resonance structure, okay, where I made two double bonds. Yes, I'm breaking the octet rule, but it doesn't matter if I'm breaking the octet rule because it's still a good resonance structure, okay? Though it goes against the rule, at least electron negative atom in the middle. Yeah. So you're gonna break the rules all the time, okay? You're gonna break the rules all the time. That's why I'm not a fan of the octet rule and the electron negativity. No, the rule that's never broken is charge conservation. Charge conservation is the only rule that is never gonna be broken. What do I mean by charge conservation? We can't have a minus charge and then suddenly explode into multiple charges. No, charge conservation is the rule that is never broken. Okay, that's why I want you guys to focus on the charges, not the octet rule, right? Okay, let me know if that clarified that, Brandon. Let me know if you have any questions about that. Okay, and then yeah. So let's discuss some other examples. What other exceptions are we gonna have? For instance, BF3. Okay, I think CL2O is PS. CL2O is PS. Yeah, no, yeah. I agree. So we're gonna have a bunch of exceptions, right? PCL5, and then I think there's some other ones in the book. So what's the exception here, chat? What's the exception here? So my BF3 is gonna have what? Boron in the center, boron. Okay, exactly. Boron doesn't need a full octet. I'm gonna put F3. Okay, so what's the name of this shape? What's the name of this shape? Do you see what shape that is? What's the name of this shape here? Okay, trigonal planar, good. So this one's trigonal planar. Okay, and then what's the name of this shape? Let's see what I'm gonna have here with phosphorus. And then I'm gonna have Cl all around it, like a starfish, kind of like that. Okay, so then I have 1, 2, 3, 4, 5 Cls. So what's the name of this funky looking shape? Let me draw that a little bit different because sometimes people can't see this. So I'm going to put phosphorus in the middle. I'm going to put two chlorines, one on top and one on the bottom. And then I'm going to put chlorine here, and then a chlorine here. Trigonal bipyramidal. Good. Good. Does everyone see that? I'm going to put a triangle here, and then a triangle here. And then on top, I have one pyramid. Okay. On bottom, guess what I have here? I have another pyramid. Okay, I have another pyramid. So this is trigonal because I have a flat plane here. The reason it's trigonal, this is my triangle here. Okay, this is my triangle right over up on this side. Trigonal bipyramidal, right? Okay. Okay. And yeah, what other exceptions we have? So let's check the table. Let's check the table. I think we've gone over most of them or a good amount of them. Which ones did we miss? Which one of these are confusing for folk? Okay. The one that's missing here is SN2. So let's add to the table. I don't know why the book forgot to include SN equals 2. So if we have SN equals 2, SN equals 2, that's called linear. That's called linear. For example, CO2. So CO2 is going to be a carbon double bonded to oxygen. Okay? So it's going to be CO2. That is called linear. Okay? And then the other ones here, which ones are confusing for people? Do we visualize the structure? Do we visualize the shape trigonal planar versus tetrahedral? Okay, octahedral. Okay, octahedral. Let's go over octahedral. Okay? So octahedral means Sn equals 6. So let's do an example, SF6. We're going to break the octet rule one more time. So let's do SF6, sulfur in the center, okay? And then I'm going to put one F on top and one on the bottom. And then I'm going to do 1, 2, 3, 4, 5, 6. So this is no longer a 3D, this is no longer a 2D structure. This is now a 3D structure. I have a square plane right here. And then I have a pyramid up on top like that. And then a pyramid down on the bottom, just like that. Okay? Now that's going to connect down over here. So the name of this shape is called octahedral. Okay? So octahedral means I have a square, I have a square plane, and then I have a pyramid up on top and then a pyramid up on the bottom. Okay? And then guys, let me plug up the channel one more time. So I went over a bunch of examples from your homework. I basically did a bunch of homework problems. So from yesterday, and go onto my channel. So let me just drop it here. So you go into my YouTube. And let me drop it here one more time. So this video, this one, the Lewis structure practice problems, those are these are the ones from your book. These are the ones from the homework. So you know how he gives you all the homework? I did like at least like 15 of the homework problems. So if I was going too fast today, like watch those ones. Watch these ones here. Okay? And then we go through like in this case, like the CLO one, okay? So you already have those ones there too. And then yeah, unfortunately that's all I have for this particular exam, but this one is like 1 hour. Watch it on times 2 speed. You're gonna finish the homework in one and a half an hour. Okay? Cool, guys. So we have about 20 minutes left. What's next? What's next? Just more? There's more problems or any more questions? What did I skip? What has he been saying? That's my question for y'all. What has he been talking about that I skipped that he's been like emphasizing it that I haven't been emphasizing it? Okay, acids. Okay, acids. Okay. So let me see here. So I think we talked about strong acids. Maybe we gotta talk about weak. Maybe we gotta talk about weak acids. Like some of these ones. Okay. Okay. So let me pull up the polyatomic ions. Let me pull up the polyatomic ions. So the next topic we're gonna do that I skipped is acid naming. Naming acids. Okay. So first things first. Polyatomic ions, acids. Okay. Diatomic. Yeah. Okay. So suppose first things first, you have to memorize your polyatomic ions. So if you can't memorize your acids, it's not because you're bad at naming acids, it's because you're forgetting your polyatomic ions. So first things first, I need to know what is my NO3 minus and what is my NO2 minus. So what is the name of this? And let's do another one. Let's do SO42 minus, and then we're gonna do PO43 minus. Okay, so I need these names, chat. I need these names. So I memorize The polyatomic ion is going to be what? This one's going to be nitrate. This one's going to be what? Nitrite. And then sulfur, I see we have sulfur, so there's going to be sulfate. And then phosphorus here is going to be phosphate. Okay? So these are just some examples here. So the next thing I'm going to do is I'm going to add an H plus. So I'm going to add an H plus to all of these. So I'm going to say H plus NO3 minus is going to react to form nitric acid, HNO3. Oh, I gave it away. Okay? And then I'm going to do H plus NO2 minus HNO2. So notice that my proton is a positive charge, and then my acid, my conjugate base is a minus charge. So I have a positive charge canceling out a negative charge, right? Right? And then I'm going to do this, I'm going to do 2H plus SO4 2 minus. And that's going to give me H2SO4. And then I'm going to do 3H plus this time, plus my PO4. 3 minus, that's going to be H3PO4. Okay. So all I'm doing is I'm adding 1 proton or 2 protons and 3 protons. And then I'm going to name all of these. So I'm going to take my base, not my base, I'm going to take my suffix here. That's going to stay the same. So I'm going to take nitrate. Okay. So if I have an 8 as my suffix, I meant to say prefix earlier. If I have an 8 as a suffix, that's going to translate into ic. Okay. So 8 translates to ic. 8, ic. Okay. And then if I have ite, it's going to be what? Chat. What's ite going to be if I translate ite? So it's going to be nitric acid. Okay, good. And then ITE is going to be nitrous acid. Nitrous acid. Nitrous. Okay, so that's going to be nitrous acid. All right. And then, all right. And then same thing for sulfur. So then we're going to do, repeat that. So what would be for H2SO4 and H3PO4? So what's the name of these acids? What's the name of these acids? Okay, sulfuric. Okay, good. Yeah, sulfuric. So I'm going to take sulfuric acid, and then what's the last one? What's the last one? Is it 8 or ite? And then what's going to be that? What's going to be that acid, guys? So I have 8. So the prefix doesn't change. So I have phosphor. So the prefix doesn't change. Very good. Phosphoric acid, right? Phosphoric acid. So 8 goes to ic, and then ITE goes to us. So I don't think I saw too many examples of naming acids. So make sure you review those because I don't think I saw too many examples of those for naming acids. Okay. And then yeah, guys. So that's naming acids, and that's going to be straight from the polyatomic ions. Also, you have these ones as well. So same idea here. Remember, same idea. So if you have hypochlorite, so it's hypochlorous acid. So 8 goes to ic, ite goes to us. Okay, ite, us. Okay, and this is 8 goes to ic, I goes to us. 8 ic perchloric acid. Making sense? Making sense? Naming ionic compounds with transition metals. Okay. Okay, transition metals. So now we're gonna do naming ionic compounds. And then guys, do we have examples in particular with transition metals? Yeah. Let me see if I can find some. Let me see if I can find some. Hold on. Okay, so like iron oxide. Okay, good question. Iron oxide. So we have to, the thing is, let me just pull some, because the thing is we need to know the number here. So we can't just do iron oxide. So what's the rule, chat? What's the rule for what's the rule for like naming ionic compounds with transition metals? What's the rule? Let me find this one. It's gonna be brown. Okay, I think this one's it. Let me find some examples here. So I'm gonna go to chapter 2, this one. Give me one sec, chat. I'm gonna pull up some examples here. From the ionic compounds. Okay, so to match charges. Okay, good. But more specifically, guys, what's the rule? The rule is I have to add the Roman numeral. Okay, if it's a transition metal, I need to add the Roman numeral. So, transition metal, I'm going to call that Tn. I need to include the Roman numeral. So the Roman numeral is going to indicate the charge. So there's only 4 transition metals. So where do transition metals live? In which block do the transition metals live? Okay, so I'm going to do, for instance, Fe2 plus. Fe2 plus, this is going to be iron 2. So this is what I mean by Roman numeral. That's the charge in Roman numeral. Fe3 plus, that's going to be iron 3. 1, 2, 3. That's the Roman numeral, right? So remember, they live in the D block. Transition elements live in the D block. And so the same idea is going to apply. We're going to call this iron 2, or we're going to call this the ferrous ion. Ferrous ion. Okay, so we have the +2. That's going to be the ferrous ion. And then we have iron 3 plus. That's going to be the ferric ion. So pop quiz for everyone. What are the names for Cu plus and Cu2 plus? So I want the Roman numeral and I want the Latin name here. So here's your example to follow along as your formula, but I want these 4. Okay, I want these 4, chat. So if I have Cu plus, what is that going to be called? What is that going to be called? Okay, good. That's going to be copper 1. That's going to be copper 1. And then the second one is going to be copper 2. Okay, copper 2. So then the Roman numeral is going to be, the lower one is going to be cuprous ion. Cuprous ion. And the second one is going to be cupric ion. Right? So the lower one goes to us, the higher one goes to ick. Okay? Yeah. Good. And then some of them, let's see what else we have here. So what's another good example that we can do here? Let me see if I find some naming transition metal ones. Yeah. That's gonna be the main idea for the transition metals. Yeah, I didn't see he had too many examples here. I didn't see too many examples, so I'm just trying to find some good ones. Okay, let's try some of these. Yeah, let's try. So if I have CaCl2, okay, or AlNO3 3, and then CuClO4 2. So we're gonna try these ones real quick. Okay, so this is gonna be naming still, naming the ionic compounds. So I have calcium. So I know my calcium is going to be living in the second column. That's why it's calcium 2 plus. And then chloride is not going to change, right? Chloride is not going to change. The only thing I'm going to change from my chlorine from INE to IDE, chloride. Okay, the only thing that changes is the IDE. Okay, similarly for aluminum, we're gonna have aluminum, okay, and then NO3, that's not going to change either. That's called nitrate. So that was my polyatomic ion for nitrate. CuClO4 okay, CuClO4 Now I have a transition metal, so what's the rule again? I need to know the charge. So if I know that this is a -1 times 2, this is a -2 charge, okay? Then this got to be what to match that, okay? If this is a -2 charge, chat, for my ClO4 minus, but I have two of those, that's -2, what does this one have to match? What does this one have to be? Good. +2, right? Good job. So this one's going to be +2. So that means that my copper +2 is going to be copper 2, copper 2 perchlorate. Or remember I said if it was copper 2, that's going to be copper, no, excuse me, cupric, cupric perchlorate. Okay? Cupric perchlorate. So it's a combination of practicing and memorizing. So don't just memorize everything fully, but you have to like practice and still memorize the rules. But like, yeah, more than anything, practice the naming and the charges. Okay? How are we doing, chat? We have like a couple minutes, we have like 10 minutes left. We have like 10 minutes left, and I'm wondering like what other like what other concerns do people have? Do you guys need like exam strategies? Is everyone good like with exam strategies? So like acting quick with it, right? You have to be quick with it if you want to like, you know, you know, you don't have too much time to think. So you have to be like really sharp and think on your toes, okay? Any other like questions? Ran out of last time. Rush through and trust your gut before going back and checking later, right? Right? Trust your gut. High key, right? Because you don't have enough time. You don't have enough time, so you have to like be quick with it. Trust your gut. Some of them are gonna be some of them are gonna be tricky questions, and some of them are gonna be freebies. So don't do the test in order. Okay, don't do the test in order. Do the test. Get the low hanging fruit. What do I mean by low hanging fruit? Get the easy ones first. Get the easy ones out of the way so you can get those points, right? Also sleep tonight. Exactly. Yeah. Yeah. Who's pulling an all-nighter? Hopefully no one. Who's pulling an all-nighter right now? Guys, don't pull an all-nighter. It's not worth it. You're gonna decrease your likelihood of you're gonna increase your likelihood of making errors. If you're really cooked, then like yeah, you have to study tonight. Okay, but if you're gonna pull an all-nighter, don't pull an all-nighter. You're gonna have to like sacrifice sleep, but you're gonna increase your chance of making errors. Brandon says I got an essay. Good luck, good luck. Okay. So yeah, guys. Oh, I just realized there's three Brandons. Okay, there's three Brandons. All right. All right. What's the difference between molecule being stable versus unstable? What's the difference between a molecule being stable versus unstable? Does it just mean it's stable if all the orbitals are filled? Um, the first thing that comes to mind, Kayla, is the resonance. So remember when we did this example? Let's see if I can find that. So molecule in terms of resonance, let me know if you mean resonance or something else. So in terms of resonance, a molecule means stable, means that we want the charges, the formal charge on the electronegative atoms to match. So what do I mean by that? In this example, we saw that nitrogen on the left-hand side had a -2 charge. That is highly unstable because nitrogen hates electronegativity. Nitrogen hates being negative, guys. Okay, versus on the right hand side, on this side, we saw that oxygen is electronegative. It has a -1 charge, so it is happy being negative. So we're gonna say that this one is more stable. So stable means that the resonance structure is gonna be more favorable compared to another resonance structure. That makes sense? Okay. So like the most electronegative gets the minus or the zero charge. The least electronegative gets the plus or the zero charge. The center atom gets zero charge. That's pretty much right. The center atom can also have a charge, but it's going to be depending what atom it is. But yeah, more than likely it's going to be neutral. Yeah, more than likely it's going to be neutral. So the most electronegative gets the minus or zero charge. The least electronegative gets the plus or the zero charge. Yeah, that's pretty much right. That's pretty much right. Yeah, exactly. You got it. You got it, Brandon. Mm-hmm. Hang on, can you quickly go over expanded octet? Expanded octet means that we're breaking the octet rule. So we went over, remember when we did PF3 versus PF5? So SF6. So how many electrons does S have here? So we have 2, 4, 6, 8. We have 1, 2, 3, 4, 6, 5, 6. We had 12 electrons. So we're like totally disregarding the octet rule. That means that we have the expanded octet. Expanded octet means we have more than 8 valence electrons. Okay? So this is going to be a memorizing thing, and it's going to be learning how to break the exceptions. Similarly, when we did PCl5 or PF5, P bonded to 6, 5 chlorine atoms. We have 1, 2, 3, 4, 5. 5 times 2, 10. So 10 is more than 8. That means we have an expanded octet. And then it's like fine and stable because sulfur has a 3D group. It's like fine and stable because sulfur has a 3D group. Yeah, now that's getting more into the theory. So why is it fine? Yeah, because good question. That's a really good question. Yeah, you're testing my knowledge here. You're testing my theory here. I'm gonna have to look into why. I'm gonna have to look into why, but I would suggest in this case, yes, always ask why. Okay, always ask good questions. Why something is stable versus unstable. But in this particular case, I don't really care about why. I just know that it's true. Okay. Does that make sense? So in this case, I know that SF6 is gonna have an expanded octet because they're telling me that I have 6 atoms bonded to one. Okay, but you're right. You're right. I definitely got to look into the theory and like truly question why SF6 gonna have a stable group. And you're probably right. It probably does have to do with the d orbitals. Yeah. Okay. Okay. So yeah, guys. So yeah, hope this was helpful. Um, yeah. So you guys have my YouTube channel. You have my website. Let me just plug the website real quick. And yeah, I'm in the Discord. I'm in the Discord, and then you guys can join my Discord if you want. And then uh, hold on, let me plug the website. And then yeah, guys. So let me know what else you're taking. So whenever you're taking like calc, or if you're taking calc or chemistry, I got you as well. So calc chem, whenever you're taking organic chemistry as well. Okay. So subscribe on the website. We got free resources, free Discord, free study sessions and stuff like that. Just like this. So just DM me. I'm super open to like doing this again in the future. So if this was helpful, all I need to know is just like please let me know if this is helpful. I'm gonna send everyone like a survey. Okay, I'm gonna send everyone a survey and then let me know what kind of do to improve in the future. And then just tell your friends to join the next review session. So we can do this for the next exam or the next final. Or if you're good for the next final, we can save this up for another class. Like let's say, well, I want to do OChem review sessions, organic chemistry, and then physics as well. Okay. And then, yeah, last but not least, if you need tutoring, I got you as well. The first session is free strategy session. You can sign up, shoot me a DM, or sign up at the link in bio. It's engineeringminds.co. Okay. Everyone, good luck on the final. Good luck on the exam tomorrow. Good luck on the midterm. And then, yeah, guys, I'm gonna post this. I'm gonna post this up on YouTube so you can rewatch it if you want to rewatch it. You guys have the slides. I have the slides here. And yeah, everyone, pretty much gonna be it. All right. Thank you, V. Thank you, Kayla. Thanks for staying the whole time. Really appreciate everyone's time. And thank you so much for like commenting and stuff. It makes it more fun for me, guys. It makes it more fun when people are commenting and making it more interactive. So thank you so much. Okay, thank you, everyone. All right, everyone. Peace out. Expect that survey by tomorrow. And then good luck on the exam. Get some rest. Good luck. Peace out.